Welcome to the lectures on the National Program on Technology Enhanced Learning sponsored by the Ministry of Human Resource and Development. The lecture series that I have been giving is on chemistry, the first year introductory chemistry to science and engineering students. The lectures have so far been on the quantum chemistry, or what I would call as the atomic description of matter as is relevant for the chemists. The last few lectures we have been looking at the hydrogen atom, and we arrived at the description of the hydrogen atom orbitals. The purpose of doing all these quantum chemical calculations, like particle in a box, particle in a two-dimensional box, the harmonic oscillator, the hydrogen atom, etc., is to understand the procedures by which we can actually study the chemistry of molecules. See, as a chemist, what is of interest from the fundamental theory point of view is how do we understand the transformation of molecules, how do we understand the formation of molecules, what is meant by chemical bonding. There are classical or what you call qualitative pictures given as early as almost 100 years ago by G.N. Lewis and then many of his scientific colleagues. But how do we understand them rigorously from the developments of quantum mechanics, which was an important development in the last century? If we are able to understand this from the atomistic point of view, then we will be in a position to predict when molecules form, what kind of stability that we can attach to them, what kind of reaction dynamics that we can expect from them, and these are not stories anymore. I mean, the computational techniques and the quantum chemistry have developed so much that today computers are used on a routine basis to do things that you would not want to do in the laboratory all the time, to do the kind of experiments that are not possible in the laboratory these days, and to study the structure of matter from the chemical transformation point of view. All of this is possible if we understand a bit about the molecular structure, for which the quantum chemistry basis is an extremely important one. The lectures so far have given you the background of the quantum mechanical tools that one has to have, and the most important tool, namely the orbitals of the hydrogen atom. The orbitals of the hydrogen atom are fundamental in one's ability to visualize molecular orbitals. I mean, be it organic chemistry or inorganic chemistry or physical chemistry, no matter what discipline of chemistry you go, the orbital description is extremely important to understand the reaction mechanisms as well as the properties of molecules. Therefore, we spent several lectures, about 4 or 5 lectures on the hydrogen atom, trying to understand them, not necessarily fully mathematically, but from how to understand the mathematical description. We may not be able to derive them. In the same spirit, the next few lectures, we will look at how the molecules form, what kind of stability that we are attaching to the molecules, how do we understand it from the chemistry point of view. Yeah, this series of lectures is from the National Program on Technology Enhanced Learning, a project funded by the Ministry of Human Resource Development, and my name is MangalaSunder. I have been giving you the last 9 or 10 lectures on the chemistry, the preliminary chemistry that all of us engineers or scientists must have. The overview of this and the next few lectures, we will concentrate on what is called the quantum chemistry for the molecules. These are the following things we will look at. One of the most important methods by which we understand molecules is the method proposed by Max Born and Robert Oppenheimer almost immediately after Schrodinger derived the famous equation, the Schrodinger's equation. The Born and Oppenheimer approximation allows us to study molecules as against the approach proposed by Schrodinger and Heisenberg, which was the study of atoms and the atomic spectrum. The approximation extends their approach to that of molecules, the formation, the stability, etc. The second most important principle, which is again a principle in quantum mechanics, is that of the superposition of wave functions or states. This is a fundamental principle. In fact, the principle of superposition of states forms the basis of introduction of quantum mechanics in the celebrated lecture series by Richard Feynman, the most well-known American physicist in the last century. The same method, when it is applied to chemistry in the study of atoms and molecules, takes the name, the linear combination of atomic orbitals, or the LCAO approximation. L for linear, C for combination, A atomic, and O orbital. The LCAO approximation. This is the basis for the molecular orbital theory. There is a parallel development in understanding chemistry through valence bond theory, and the valence bond theory is, of course, a nice mathematical description of a more qualitative picture developed earlier, known as the valence shell electron pair repulsion theory, VSEPR, which many of you must have studied in your high school on the basis of the electron dots. The valence bond theory also leads, as an extension of some of the ideas, to the idea of hybridization, or how the atomic orbitals or the molecular orbitals are oriented in space. It's an extension of the valence bond theory. And of course, today, the most familiar method to chemists is the linear combination of atomic orbitals, which is the basis of molecular orbital theory. These are all described in some detail. And application of those methods, the methods I've just described, to chemical bonding, we will study some of the simplest molecular species, the hydrogen molecule ion. It's two hydrogen atoms with one electron. It's a H2 plus ion, probably the simplest molecule that one can form. That is a molecule with only one electron. And you would be surprised that there is a sufficient amount of mathematical details which go into the understanding of molecule ion. This can also be extended to the study of one of the most well-known molecular species, also the simplest one, the hydrogen molecule, H2. The molecular orbitals, the concept of molecular orbitals as developed from these two, will be applied further to the study of other homonuclear diatomic molecules, that is diatomic molecules in which both the atoms are the same, helium dimer, lithium dimer, beryllium, and so on, to understand a little bit about the progression of these ideas. We will also study a little bit about the molecular orbitals for the heteronuclear diatomic molecules, that is molecules in which the two atoms are different. For example, carbon monoxide, hydrogen chloride, things like that, in which the atoms are not the same, heteronuclear. This cannot be carried out in detail to the study of polyatomic molecules without the mathematical background. Therefore, what we will try to do in the case of polyatomic molecules is to reiterate the valence bond description that you are familiar with, and giving you a little bit about how the mathematics is, the quantum physics describes the corresponding principles here. And the same thing will be done with the molecular orbital description. And if time permits, I will introduce you to one of the most well-known program for calculating the molecular orbitals in chemistry, the program for studying the molecular structure in chemistry, the stability in chemistry, the program known as the Gaussian, for which the discoverer and all his colleagues, through the efforts of John Pople, formerly professor of chemistry in Carnegie Mellon University, and John Pople came up with a procedure for studying the chemistry of the molecules through the computer, and the method that he proposed, known as Gaussian, was eventually recognized by the Nobel Committee, and he won the Nobel Prize. He shared it with another physicist, Walter Kohn, a few years ago for his discovery of the computational methods in chemistry. So we will try and introduce a little bit of the Gaussian program. There are similar programs available in the literature. You will get a brief exposure to that, so that the study of the molecular structure is a fairly serious business, as you will understand. a little bit about the introduction of computational chemistry and its applications will be described, and also how we follow through the computational chemistry web portals, the websites which contain more information about the computational chemistry, etc., will be given in this series of lectures. Now let's get to the lecture today, namely the lecture on the Born-Oppenheimer Approximation. Let me call that as Molecular Quantum Chemistry 1 in the module on quantum chemistry. The Born-Oppenheimer Approximation and the principle of superposition is what we will look at today. Okay. First of all, when we talk about approximations, just recall from your elementary background, what do we mean by an approximate solution to a mathematical problem? Okay. I'll give you two simple examples so that you can recall that there are procedures for doing this systematically. Okay. Let me start with a simple series, a function of x1 plus 1 by x plus 1 by x square plus 1 by x cube, etc., all the way up to infinity. This is an infinite series. Okay. For certain values of x, of course, this infinite series converges to a value, to a finite value, and for x is equal to 1, for example, there is a problem here. We'll not worry about this, but wherever the series exists, the closed form solution for this series, you understand from high school algebra, is given by 1 by 1 minus 1 by x. Okay. That's when you, it's easy to see that that is the closed form analytic solution, and obviously it's not valid for x is equal to 1. But what do we mean by, in this case we know the final solution, but we will see what is meant by an approximate solution to the series. Okay. If you truncate the series to several terms for a certain value of x as an example, if you truncate the series by the first two terms, you will get a value. Truncate this to the third term, you will get another value, and so on, and that's what is given here in this table. So when you truncate it to the first term 1 by x, the value for x is equal to 2 is 1.5. The next term 1.75, next 1.875, 1.9375. It keeps on closing towards or convergent towards the exact value. When you put x is equal to 2 in this expression, you know 1 minus 1 by x is equal to 2. Okay. So the exact value is 2, but the approximate method of truncating this series, if we did not know this formula, converges slowly towards the value x is equal to 2. This is what you mean by approximation in this case. Another example, the previous one is a relatively easy exercise, but slightly more complicated example. Let us calculate the value of the integral exponential of minus some constant times x square dx. C is a constant, and the exponential is the integral is calculated between x is equal to 0 and x is equal to a finite value a. Okay. It is not possible to derive a closed form analytic solution for this integral when a is finite. In fact, this is related to what is known as the error function integral in mathematics. But if x is infinity, you will be surprised that there is an analytic solution to that. When x is infinity, the analytic solution is 1 by 2 root pi by c, whatever is the constant here. Now let us try and find out how closely that this integral approximates as a increases to very large values and eventually to infinity. So here is a table which gives you the numerical value for the same integral with c equal to 1, exponential of minus x square dx. So when a, the upper limit is 2, the value of this integral from numerical procedures is 0.882081. When a is 3, closer to the infinity, between 2 and 3 it is not much, but you will be surprised that as far as this function is concerned, when a is equal to 3, it is almost close to the exact value 0.886207. Now you put a equal to 10, it looks like the integral does not change by much. See, it is 886.227, the decimal point, fourth decimal point. So the approximate value for this integral numerically that can be obtained for a is equal to 10 is to this level of truncation in decimal points is the same as when a is equal to infinity, for which we know the analytic solution is root pi by 2 is 0.886227. Okay. So what we mean by approximation is that we try to truncate, or we try to take certain simple limits to evaluate the function as accurately as we can. Okay. So different degrees of approximation chosen, and that depends upon the desired level of accuracy. See, the one nice thing about this particular example is that in both cases we know the exact value, and therefore we see how quickly our approximate values reach the exact value. In real life, in quantum mechanical problems, in quantum chemistry problems, we do not know what the exact value is, because we just cannot calculate them analytically. Hydrogen atom atomic orbitals could be calculated analytically with all those functions I described, and hydrogen atom is probably the last in quantum mechanics for which exact solution could be given. For all the others, we do not know what the exact solution is or what the exact value for the functions are at various points. Therefore, we have to have procedures which ensure that we are approaching the exact value somehow, mathematically correct procedures. Okay. Analytic exact methods are very few. Approximate methods for solving quantum chemistry problems are the order of the day. That is, those are the only ways by which we know how to study the system. The example of the Schrodinger equation for an atom with more than one electron, it is not possible to solve by analytic means. One has to solve this by approximate methods. Perhaps the approximation is very, very good, but it is not analytic. Schrodinger equation for polyatomic molecules, there is no chance that one can study them by analytic methods. One has to devise procedures by which the algebra could be carried up to a certain point, and beyond that one has to study the algebra through its implementation in a computer using a numerical program and so on. Okay. So they have to be solved by approximate methods, and the most important approximation in all of quantum chemistry, I would even say, in understanding the molecular structure, came by Robert Oppenheimer and Max Born. Max Born, you already were introduced. He gave the interpretation for the wave function in terms of the probabilities, the absolute square of the wave function being related to the probabilities. Robert Oppenheimer, an American scientist, American physicist, was associated with Max Born in the early days of quantum mechanics development, and both of them devised a procedure by which the Schrodinger equation could be approximately solved for the molecular problems. If you do not know, Robert Oppenheimer also was the leader of the Manhattan Project in the United States during the Second World War, which eventually led to the development of the atomic bomb and which brought an end to the Second World War. Robert Oppenheimer was the head of the team, which consisted of physicists, chemists, and many engineers, and he was very well known for his contribution for bringing the Second World War to an end. Of course, the atom bomb came out of that as a result. The Born-Oppenheimer is a method for solving the Schrodinger equation in the case of polyatomic molecules. Let me explain the mathematical procedures in a few minutes. The procedure gives a method for separating nuclear motion from the electronic motion. We never discussed this in the case of hydrogen atom. In the case of hydrogen atom, we looked at the electron, the motion of the electron. We never considered the motion of the proton, the nuclear motion. It was implicit that the origin was fixed at the proton and the proton did not move. Okay. It was an approximation we already used, even though it is not necessary to use that approximation. The proton-electron problem in the case of hydrogen atom is a two-body problem. In physics, two-body problem can be separated into a center of mass and a relative coordinate problem. And it's possible to solve the hydrogen atom problem exactly by taking into account the hydrogen nuclear motion. We did not do that. If we did that, all our masses that we use to calculate for the electronic motion should be replaced by the reduced mass of the electron-proton system. That was the only thing that was needed. Now, in the case of molecules, it is important to recognize that there are many nuclei, there are many electrons, and the nuclei move with a certain amount of kinetic energy. The electrons also move with a certain amount of kinetic energy, and the nuclear electron system involves many terms: the nuclear kinetic energies, the electron kinetic energies, the nuclear electron interaction energies, the electron interaction energies, many of them. Therefore, in this mess, how do we separate the Schrodinger equation to a problem that is solvable was first proposed by Born and Oppenheimer, and it is a procedure for separating nuclear motion from the electronic motion. The nuclear motion is assumed to be slow and the electronic motion is fast, and as a result of their method we also get the new concept, the concept of potential energy surfaces for molecular motion, and this is fundamental to the understanding of reaction dynamics, chemical reaction dynamics from quantum chemistry. So there are certain advantages to using the Born-Oppenheimer procedure in that we can develop the potential energy surfaces for molecules. Now, why is this possible? Please recall that the mass of the electron is of the order of about 2000 times less. See, the mass of the electron is 9.10939 times 10 raised to minus 31 kilograms. The mass of the proton in a typical nucleus 1.67262 into 10 raised to minus 27 kilograms. The mass of the proton, any nucleus containing x number of protons, you simply multiply this. The mass of the neutron is pretty close to that, but what is important is the proton to the electron mass ratio is about 1836. Now, if you assume that the molecules have approximately the kinetic energy of say 3/2 kT, and if this energy were to be equally distributed between the nuclei and the electrons, now one can make a simple estimate, namely that the kinetic energy of the individual species is mv square by 2, half mv square. For the electron also half mv square. If you look at that, you see that the masses of the proton and the masses of the electron are such that for the same kinetic energy for both, you see the nucleus moves much more slowly than the electron because of the very large mass. This is the first important issue in deciding how do we set up the molecular wave function. Electrons move generally much faster than the nuclei, and therefore it is possible to separate the electronic motion from that of the nuclear motion. Okay. Anyway, let me explain that now by first let me introduce Max Born through the pictures here and Robert Oppenheimer. The proposal was given in 1927 through one of their most celebrated papers in quantum chemistry, and let's get to see what the approximation means. Okay, so let me take a simple case of two nuclei and one electron. A fictitious case, but we will see what is meant by the approximation. So this is proton 1, proton 2, and this is the electron 1. So now if you look at the Hamiltonian for this system, it contains, the Hamiltonian contains kinetic energy of the two nuclei P1, proton 1 and proton 2, like two hydrogen atoms with one electron, so it is like a H2 plus. If you want to think about it, give a physical representation to this model, it's like the hydrogen molecule ion. So you've got the two protons and the electrons, and if we mark the distance between them, or 1e and or 2e, and let's call this r12, so that you have the appropriate distances, and these are all charges. It's positively charged, this is negatively charged, positively charged. Therefore, the potential energy of this system of three charges is the Coulombic attraction as well as the repulsion terms, and the kinetic energy is the kinetic energy of the individual species, this proton, and this electron. So if you write down the Hamiltonian for this system, it is minus h bar square by 2mp proton 1, and you recall from the hydrogen atom that we were writing dou square by dou x 1 square, let us call it P1, this 1 corresponds to the proton 1, plus dou square by dou y 1 square plus dou square by dou z1 square. All of this is the kinetic energy term in the quantum mechanical form for the proton 1, and likewise for the second proton also you have got the kinetic energy h square by 2mp, again dou square by dou x2 square, these are the coordinates of the second proton, dou y2 square plus dou square by dou z2 square. These are the two kinetic energies of the two protons. Is not enough, is not complete. Then we have got the electron kinetic energy, which is minus h bar square by 2me. This is, you are familiar from the hydrogen atom, and let me write this as dou square by dou xe square to indicate that this is the electron energy term. Basically this is the momentum along the x coordinate for the electron, momentum square, p square by 2m. You recall the quantum that we have been doing so long. Dou square by dou ye square plus dou square by dou ze square. Okay. So we have got, for this 3 particle system, we have got 9 coordinates, x1, y1, z1 for particle 1, proton 1, x2, y2, z2 for proton 2, and the xe, ye, ze for the electron. This is only kinetic energy, but what about the potential energy? All of this is kinetic energy. What about the potential energy? Potential energy is obviously minus E square by 4 pi epsilon naught. Let me write it in the next page. Minus E square by 4 pi epsilon naught. Remember that the model we have is proton 1, proton 2, R1 2, R1 E, R2 E. If I remember, that's what I wrote, did I? Yes, R1E, R2E. So what you have is, for the proton electron attraction here, you have got minus E square by 4 pi epsilon naught R1E, and this proton electron attraction you have got the other term minus E square by 4 pi epsilon naught R2E, and the proton repulsion, they are both positive charges, as plus E square by 4 pi epsilon naught or 1 2. So you have got how many terms? 9 terms in the kinetic energy in a 3-dimensional coordinate system, and 3 terms, all of which involve, this R1E involves the square root of this, the difference between these two x coordinates, y coordinates, z coordinates, etc. So it is a fairly complicated expression, and therefore solving this, if you call all of these things as the h as the sum of potential energy plus the kinetic energy, you have got the solution that you have to worry about is h psi is equal to E psi. What is psi a function of? Massive. It is a function of x1, y1, z1, the coordinates of the proton 1, x2, y2, z2, the coordinates of the proton 2, and xe, ye, ze, the coordinates of the electron. So psi is a function of these 9 coordinates, and the Hamiltonian contains derivatives of all these 9 coordinates with respect to these, as well as the interaction energy. Therefore you see that the problem is intractable. I mean, cannot be solved analytically. This is for hydrogen molecule ion. What is the case of hydrogen molecule? Typically for a hydrogen molecule, if you want to solve the quantum problem, you have got 2 protons and 2 electrons. Okay. Proton 1, proton 2, electron 1, electron 2. And if you compute the number of terms, for this proton there is a kinetic energy term, 3 of them, 3 of them, 3 of them, and 3 of them. So there are 12 coordinates which are part of this, and the interaction energies are now the repulsion energies between the 2 protons, the repulsion energies between the 2 electrons, the attraction between this proton and this electron, this proton and this electron, this proton and this electron, and this proton and this electron. See, it is an interplay of all these interactions which one has to understand as determining the stability or the formation of the hydrogen molecule. Therefore, the problem becomes more and more computationally difficult, and therefore some approximate methods are needed right away. The moment you write the solutions for the hydrogen atom, you know that it cannot be taken over directly to that of the hydrogen molecule or even the hydrogen molecule ion in the simplest case. So the first approximation that Born and Oppenheimer made was the following. With respect to the solution H psi is equal to E psi, one has to separate the psi in terms of a psi nuclear and a psi electronic. You recall that we are very fond of separating the wave functions in terms of the various coordinates involved. Hydrogen atom, you have separated the x, y, z problem by writing it in the spherical polar coordinates. Last 4 lectures were summarizing that. Radial coordinate and the angular coordinates and so on. So separability of the wave function is important in solving the differential equation as simply as possible. Therefore, the separability of the wave function here, one starts with the psi nuclear and psi electronic, but with the following in mind, namely nuclear motion is slow, electronic motion is fast. Therefore, what one assumes is that the psi electronic wave function is a function of all coordinates. All coordinates in the case of hydrogen molecule ion, all the 9 coordinates for H2 plus, all the 12 coordinates for the H2. And if you think about carbon 60 fullerene, you wanted to understand the stability from solving the Schrodinger equation, you have got 60 carbon atoms and 360 electrons. So you have got 420 species into 3, that many coordinates. Okay. You know, one should be mad, but people have solved such problems anyway. So the psi electron, the electronic wave function is a function of all these coordinates, but the nuclear wave function is a function of only the nuclear coordinates. What is the basis for this? The basis for this is the fact that the proton to the electron mass ratio is so large that the proton or the nuclei, which in this case will be the number of protons plus the number of neutrons, multiplying by approximately this number, and you see that the separation tells you the following. Physically, one has to visualize it this way. As the electrons, as the nuclei move, I mean they undergo vibration, they undergo rotation, the molecule in any finite temperature has many possible motion, translational motion, rotational motion, and relative to each other they undergo vibrations. As the nuclei move, the electron motion associated with the nuclei is much faster than that of the nuclei, that the electrons instantly readjust themselves to the new nuclear positions. The electronic wave function does depend on where the nuclei are, whether they are this far away or whether they are this close, because if they are this far away there may be no interaction, there may be no molecule, they may be local atoms, but when they come together the molecule is formed, there is some stability attached, therefore the electronic wave function does depend on the nuclear positions, the nuclear coordinates. On the other hand, the nuclei do not necessarily feel the electron because the electrons instantly readjust themselves, therefore the nuclear wave function is not dependent, the nuclear wave function is not dependent on the electronic coordinates as assumption 1. Therefore, if we denote all the nuclear coordinates as R1, let me write out the coordinates. If we, in our case for the hydrogen molecule ion, let us go back and do this for the hydrogen molecule ion, the psi nuclear is a function only of the nuclear coordinates, namely x 1 y1 z1 x2 y2 z2 and is independent of the electronic coordinates, the molecule ion, the third particle, whereas the psi electron is a function of all of these x1 y1 z1 x2 y2 z2 and xe ye ze. Okay. So the overall psi is a function of psi nuclear times psi electronic, step 1. Okay. What is the next step? When you apply this to the Hamiltonian, see, this is a proposal. The proposal is psi electronic times psi nucleus. Okay. Now with this proposal we solve the Schrodinger equation H psi is equal to E psi, which means H psi electronic psi nuclear is E, a constant independent of all these coordinates, psi electronic psi nuclear. Okay. Now if you look at the form of H, it has minus h bar square by 2 m p. Let me write the overall derivative for the nucleus 1 as del 1 square. Okay. Del 1 square is obviously dou square by, no, you can erase this later, del 1 square is dou square by dou x1 square plus dou square by dou y1 square plus dou square by dou z1 square. This is del 1 square. This is the nuclear motion for the first nucleus, and del 2 square is the corresponding one. You can simply replace 1 by 2, 1 by 2, 1 by 2 here. So you see that the two Laplacians, as they are called, corresponding to the kinetic energy of the two nuclei, and minus h bar square by 2 m e del E square, which is the corresponding energy, kinetic energy term for the electronic motion. What is del E? You can easily write this del E as nothing but the x E square and so on. You erase all these things and you have got del E square is x E square, y E square and z E square. So this is, if we use this notation, it's sort of clear. Now you see this is a derivative containing only the nuclear coordinate 1. This is the derivatives containing only the nuclear coordinates 2, and this is a derivative set containing only the electronic coordinates dou square by dou x E square. That's extremely important in the next approximation that they used. Okay. So let me erase this del E. Remember that that's what they stand for. Now if you apply del 1 square to psi nucleus and psi electron, you have to solve this equation, because after all H psi is equal to E psi is what we want to solve. Therefore when you operate H psi, you are going to get one term like this. You are going to get another term corresponding to del 2 square psi nuclear psi electronic, and also the third term involving the derivative. You will get del E square corresponding to psi nuclear and psi electronic. Now this individual terms as you have them here. Now if you go back and look at the approximation about the wave function, namely psi nuclear depends only on the nuclear coordinate. Okay. Psi electron, it depends on all of them, electronic and the nuclear coordinates. Let us see what the derivatives do without evaluating the derivatives. Del E square on psi nuclear will contain, you have to remember the UV formula. You recall d square by d x square on a function say u of x v of x, okay, a function of a product of two functions. What is the derivative? Even let's not even do dou square, but let's do just a dou by dou x. What is dou by dou x on ux vx? It's going to be u dou v by dou x plus v dou u by dou x. Okay. Two terms are there from elementary calculus, you know this for partial derivatives, and if you have to do this for the second derivative, dou square by dou x square on uv, you see you are going to get u dou square v by dou x square plus 2u du, sorry, 2 du by dx dv by dx plus v dou square u by dou x square. So you are going to get the terms which are the derivatives of both these functions. Here you have got psi nuclear and psi electronic, and this is the electronic derivative. Psi nuclear does not contain any electronic coordinates, therefore this derivative does not act on this, it only acts on psi electronic. So this is extremely simple, that del square E on psi nuclear, psi electronic is psi nuclear times del square E on psi electronic, no problem. Okay. So this is simple enough, but the next term is the harder one, del 1 square nuclear 1 of psi nuclear and psi electronic. You are going to get these derivatives. Now this is a function of the nuclear coordinates as well. This is a function of the nuclear coordinates only. Therefore what Max Born and Robert Oppenheimer chose to write was basically this as psi electronic del 1 square psi nuclear. What are the terms which are being dropped out when you write like this? Go back and see the product rule. Okay. If there is a derivative of x with respect to two functions here with respect to x, when you take the derivative of a product, you see there are terms u d square v by dx square, 2 dou u by dou x dou v by dou x plus v dou square u by dou x square, and so on. Now what you have assumed is this to be independent of x for the purpose of taking the derivatives, not as a function, for the purpose of taking the derivatives. When you say that v is independent of x, obviously this derivative you are going to throw away, dou v by dou x, and you are going to throw away this derivative, dou square v by dou x square, and therefore you approximately write this as v times dou square u by dou x square. Please remember, when you write del 1 square psi electronic psi nuclear as roughly psi electronic del 1 square psi nucleus, what are you doing? You are throwing away the dependence of psi electronic on nuclear coordinates only for the purpose of the derivatives, only for the purpose of derivative calculation. That is, the variation, to be very precise, the variation of psi electronic as a function of the nuclear coordinates. As a function of the nuclear coordinates. Okay. You are not throwing away, or you are not making the approximation that psi electronic is independent of nuclear coordinates. No. You are only saying that the function, the electronic wave function, is a function of nuclear coordinates, but its rate of change with respect to nuclear coordinates is negligible compared to the rate of change with respect to the electronic coordinates. The rate of change of the electronic wave function with respect to the nuclear coordinates is negligible. The function itself is a function of nuclear coordinates, but its rate of change with respect to the nuclear coordinates is not 0, but it is negligible compared to all the other rates of changes. Not only the rate of change, but also the second derivative, the what is called the dou psi electronic with respect to dou nuclear coordinates and dou square psi electronic with respect to the dou square nuclear coordinates. You are throwing these terms away as approximately small compared to the other derivative terms, compared to the other potential energy terms. This is the sum and substance of the Born-Oppenheimer approximation for the entire molecular chemistry program. Let me write that again in words. The wave function psi electronic is a function of nuclear coordinates. And electronic coordinates. You are not saying that it is not. This was the first step. But what is being thrown away is the dou psi electronic with respect to dou x1 or dou psi electronic with respect to dou y1, dou psi electronic with respect to dou z1. All of these are nuclear coordinates of nucleus 1, okay. And dou psi electronic with respect to dou x2, likewise the other two terms. You throw away these as unimportant, not significant. You do not make them as 0. If you make them as 0, automatically the interpretation is that the wave function itself is independent of the coordinates. That is not true. The electronic wave function does depend on the nuclear coordinates. Otherwise, the molecular formation cannot be explained. The electron densities keep changing as the two nuclei come together. The electronic densities are described by their position at whatever the space is. Therefore, they are dependent on where the nuclei are, how close they are, how far away they are, how far apart they are. All these things are important. You are not neglecting the dependence of the electronic wave function as a function of the nuclear coordinates. What you are doing is you are neglecting the variation, the derivative of the electronic wave function with respect to the nuclear coordinates, the first derivatives and the second derivatives, both of them. Dou square psi electronic by dou x1 square, all the other two other terms, dou square psi electronic with respect to dou x2 square and the corresponding two terms. These are the terms that you neglect. Okay. What is the outcome of this? Now let us write the algebra very quickly. Therefore, H now contains an operator, let me write this, an operator T for the nuclear kinetic energy containing the derivatives, an operator for the electron kinetic energy, a sum of various terms. It also contains the electron nuclear attraction kinetic potential energy, sorry, not T. Let me write this as the usual notation is the V electron nucleus plus the V nuclear in this case. Since there is only one electron, we do not worry about any further term. These are the only terms which are present. Now H psi electron, psi nucleus, when you write this as E times psi electron times psi nucleus, okay. What do the kinetic energy terms do? You have T nuclear plus T electronic plus V electron nucleus plus V nucleus acting on psi electronic psi nucleus as E times psi electronic psi nucleus. We will do the algebra quickly. Now T nuclear on psi electronic, we have made this several times. T nucleus does not change the psi electronic but only changes the psi nucleus. Therefore, what you have is T nucleus psi nuclear, and the psi, maybe it is better to write it with the psi electron in front. Let us do the psi electronic. This is the first one, T nuclear psi nuclear. And the electron term, of course, the kinetic energy has only derivatives of this. This is independent of the electron coordinates. Therefore, the second term is very easy, namely it is psi nucleus T electron psi electron. Kinetic energy term, let me keep this in focus, plus we have talked about the kinetic energy plus the potential and the two kinetic energies plus V electron nucleus acting on psi electron and psi nucleus plus V nuclear V nuclear acting on psi electron psi nucleus is equal to E on psi nucleus and psi electron. Okay. When you do this, what happens is it separates the Hamiltonian equation that we have here, the differential equation, into two sets. One set corresponding to the electronic motion only and another set corresponding to the nuclear motion only, and the electronic motion problem, when it is solved for a given set of nuclear coordinates, it is called the electronic energy solution or the quantum chemistry problem. When you solve this set of equations for the nuclear motion, you are studying this as the dynamics of the nuclear motion, and this is what constitutes the branch of spectroscopy. So let me summarize this. So what you have is a psi nuclear times T electronic psi electronic plus a V electron nucleus psi electronic. I am just rearranging those terms, plus you have got a psi electronic times a T nuclear psi nuclear plus V nucleus psi nuclear. These are the terms, when you rearrange them, is equal to H psi electronic, is equal to E. This is, all of it is H so far on the left hand side. This is the E psi electronic psi nucleus. Okay. Now if you look at this particular form, here is the wave equation corresponding to the electronic kinetic energy operator, the electron nuclear potential energy, both of which depend on the electron coordinates. That is a wave function which depends on the electron coordinates. The solution of this becomes the solution for the electron problem for a particular set of nuclear coordinates. Now if you vary this nuclear coordinates to next set to some other values, you will have another equation to solve. You solve this electronic problem for every set of possible nuclear coordinates, and once you have solved them, the solution of this problem will be the energies for each set of nuclear coordinates. Therefore this equation becomes psi nuclear times an energy which is a function of the nuclear coordinates times psi electronic. This is the Schrodinger equation for the electron problem. This particular T electron psi electron V electron nucleus psi electron is the Schrodinger equation for the electron problem, and it gives you for every value of the nuclear coordinates which determines this potential energy an E nucleus times a psi electron, and this has to be added to this term, the psi electronic T nucleus. When you add this term, let me highlight this particular one. Let me see this psi nuclear problem, this particular term. When you add to the remaining term in this, gives you the nuclear solution to the Born-Oppenheimer problem. Therefore, what you have in summary is that the overall Hamiltonian for the electron nuclear problem involving many atoms and many electrons is separated into two equations of motion, one for the electronic motion alone, but the energies that come out of the electronic motion are dependent on a set of nuclear positions, because VE nuclear is there, the nuclear coordinates are there. If you vary the nuclear coordinates to another set, you will solve the same equation, you will get another energy. Therefore, you get many such energies, and when you solve for all these energies, the final that you get is the electron energy as a function of the nuclear position. Use that to solve the remaining nuclear coordinates problem, and that is the spectroscopy problem, because spectroscopy deals with nuclear motion, rotational motion, vibrational motion. To solve for the nuclear spectroscopy problem, you need to solve the electronic motion problem, and this is what you call as the quantum chemistry. Therefore, Born-Oppenheimer approximation allows you to separate the overall chemical problem into a static stationary energy solution problem, that of the electronic motion, and a dynamical problem, that of the motion of the nuclei, in the presence of an overall potential generated by this electronic motion, and that leads to the concept of the potential energy surface. Let me continue this in the next lecture for the first 20 minutes or so and give you an expression on the potential energy surfaces, and then we will go ahead with the superposition of the molecular functions, the atomic orbitals, and complete that part of the lecture. Until then, thank you.